acetic acid, which has been written in a kind of strange way. Acetic acid, which is also can be written like this. So the solution is going to be conducting or non-conducting. Most likely it's going to be conducting, although probably weakly because acetic acid doesn't really dissociate that much. The solute is ionic to an extent, and so the best symbolic representation is this one, where it's going to be very weak. It will conduct. It will conduct. It's just very weak. You can also write it out like this. Plus H plus. Okay. Ammonia. Ammonia is a weak base. So the solution is it going to be conducting or non-conducting? It's going to be strong, weak, or non-electrolyte. So it's going to be relatively non-conducting. It lies somewhere between the weak and non-electrolyte. It's somewhat similar to the acetic acid situation that we just had. Probably going to be a non-electrolyte. Solute is molecular. Best symbolic representation is NH3 aqueous. Solutes in aqueous solution. So here's a flow chart of what to do. So if we have a solute in an aqueous solution, first of all, we have to see if it is an ionic compound or molecular compound. So if it's an ionic compound, then these are strong electrolyte ions. If it is a molecular compound, we then need to determine if it is an acid or a base. So acids are like acetic acid, or sorry, acids and weak bases. So strong acids, such as HCl, they give strong electrolyte ions. So HCl is an example of a strong acid, which gives strong electrolyte ions. Acids and weak bases then, so weak acids and weak bases, so these give weak electrolyte molecules and ions. So let's take a case such as our NH3 and our acetic acid, our CH3COOH. Then the other one, molecular compounds, if we have most molecular compounds, such as our sucrose that we saw earlier, these are non-electrolyte molecules. They do not dissociate at all. They do not produce ions in solution at all. Whenever I say dissociate, what I mean is they separate into, like for sodium chloride, it's separating into sodium plus and chloride minus. Those things like sucrose don't do that. And so those are non-electrolyte molecules. Conductivity properties of pure substances, so solids, metal spatula, a wooden spatula handle, sodium chloride, sucrose. Pure substances, metal spatula. Metal generally conducts electricity really well because the structure of metals, as we've seen before, is that the cations and the nuclei are kind of associated into like a lattice. So like they're into like an array that's regularly repeating, not very much like what I've drawn, but you get the idea. And then this is surrounded by a sea of electrons. And so that sea of delocalized electrons can conduct electricity. So metal spatula is conductive. Wooden spatula handle is not conductive. Cellulose is a molecular compound. It doesn't have ions or ability to conduct electricity. So that's why wooden things do not conduct electricity. Sodium chloride will conduct electricity, just not very well. And then sucrose will not conduct electricity. Liquids such as water do not conduct electricity. Reactions in aqueous solution. So here we need to distinguish between ions and molecules. Ions are like sodium chloride, molecules are like sucrose. What predicts a reaction? What is the driving force of the reaction? So we need to think about what is happening here. Are we going, are we going from a place of, are we increasing entropy in the system or disorder, like Are we producing a lower energy state? What is happening? The formation of a precipitate, an insoluble solid, is usually a good driving force. The formation of a gas as well. So like the release of CO2, formation of a precipitate. So if we recall back to our calcium chloride and our sodium hydrogen carbonate reaction, the driving force there was the formation of the precipitate, so the calcium carbonate, and also the formation of a gas, which was the carbon dioxide. So both of those were driving forces in the reaction to basically push the reaction towards the products. The formation of a weak electrolyte is also a good one. Solubility rules. How do we know if a compound will be soluble in water? For molecular compounds, the molecules must be polar. So molecular polarity, we've already covered that in some detail in module 4, which was chapter 8 of the book. For ionic compounds, the compound solubility is governed by a set of solubility rules. So here are water solubility rules for ionic compounds. So soluble compounds are almost all salts of sodium, potassium, and ammonium. So Na plus is sodium ion, potassium ion, and ammonium ion. Salts of nitrates, chlorates, perchlorates, and acetates, these are all water soluble as well. Almost all salts of calcium, chlorides, bromides, and iodides. Exceptions that are not soluble are like silver chloride, mercury 2, or like dimercury 2+ ion, and lead chloride is not soluble. Salts containing F- except for these. So magnesium fluoride, calcium fluoride, strontium fluoride, barium fluoride, and lead fluoride. And then sulfate ions, like sodium sulfate is soluble in water, but other ones such as calcium, strontium, barium, lead, and silver sulfates are not. So if one ion from the soluble compound list is present in a compound, then the compound is water soluble, except for the exceptions. So generally, like these are all always soluble. Most of these are soluble. Some of these are soluble, and some of these are soluble. Mostly, like you can see that it's the group 2A ions, so magnesium, calcium, strontium, barium. Lead is not in group 2A, but so it's sort of those group 2 plus lead. And in the case of the sulfate, including the silver as well. Water solubility of ionic compounds. So here are some insoluble compounds. So most carbonates, most phosphates, most oxalates, chromates, and sulfides. The salts of, however, the exceptions are the salts of ammonium and alkali metal cations. So that's group 1A, alkali metals, group 1A. So it's like sodium and so on, sodium and lithium and so on. So sodium carbonate dissolves in water, sodium phosphate, lithium oxalate, those things, they all dissolve in water. Potassium dichromate, potassium chromate, those all dissolve in water. Most metal hydroxides and oxides also dissolve, except for alkali metal hydroxides and barium hydroxide and strontium hydroxide. If one ion from, these are mostly insoluble except for the alkali metal hydroxide. So for example, sodium hydroxide dissolves in water. Calcium hydroxide does not dissolve in water. So if one ion from the soluble compound list is present in a compound, then the compound is water soluble. I'm not quite sure yet if we'll give this as in the quizzes as like as part of your periodic table and stuff. It has been done in the past, but I need to check with the other instructors. Chemical reactions in water, exchange reactions. So here we have an exchange of X and Y. So AX plus BY gives AY plus BX. So these sorts of anion exchanges are quite common in water. So usually it creates the like weaker salt, or it creates a system which is more stable, or it induces the precipitation of something. So the ions exchange places between cations, and a precipitate forms if one of the products is insoluble. Precipitation reactions to the driving force is the formation of an insoluble solid called a precipitate. So lead nitrate plus potassium iodide gives potassium nitrate plus lead iodide is a precipitate. So barium chloride plus sodium sulfate gives barium sulfate plus sodium chloride. So barium sulfate here is a precipitate. That's shown by this S, meaning it's a solid. And precipitates are determined from the solubility rules. So if we went back to our solubility rules, we would see the barium sulfates are insoluble. And so you get something like this happening. So as you pour in one of your solutions, like for example, the barium chloride into the sodium sulfate, you will see that you will form this white cloud, and that is caused by the formation of the barium sulfate in that case. Here are some others. So precipitation reaction is a reaction where an insoluble solid precipitate forms and falls out of solution. So we have lead chromate on the left-hand side here, which is from a solution of lead nitrate and potassium chromate. Then we have a lead sulfide from lead nitrate solution being added to ammonium sulfide. So you can see here that we have formed the lead sulfate. Iron hydroxide from iron chloride and sodium hydroxide. And then here we have silver chromate, which is insoluble, formed from silver nitrate and potassium chromate. So you can see like the formation of the precipitate happens almost instantaneously, because that is a very strong driving force for the reaction, is this formation of a precipitate, which helps to stabilize the system actually. So some definitions then. So complete equation, or a molecular equation, is an equation in which all substances are written as if they were molecular substances, even though some may actually exist as ions in solution. An ionic equation is an equation for a reaction involving ions in solution in which soluble substances are represented by the formula of a predominant species found in the solution. Spectator ions are ions in an ionic equation that do not take part in the reaction. So thinking back to our calcium chloride and our sodium hydrogen carbonate reaction, the spectator ions there were the sodium and fluoride, because they didn't actually participate in the reaction in any meaningful way. The net ionic equation, so an ionic equation from which the spectator ions have been removed. So here are our solubility tables, which tell us about our soluble compounds and our insoluble compounds. Here we have silver compounds, some of which are soluble and some of which are not. So silver nitrate is soluble because most nitrates are soluble. So remember, whenever we have these two tables, if one of the ions is soluble, the whole thing will be soluble. It needs for both of them need to be insoluble generally to kind of override that. So the silver chloride is insoluble. That is an exception to this rule. So there are, like, whilst that rule exists, there are some exceptions to it, and they're in the yellow boxes. And then silver hydroxide, some of which is soluble, but some of which is not. You can see here there's like a little pile of silver hydroxide here. That's the insoluble part, but some of it, a very, very small amount, can dissolve. So nitrates are generally soluble, as are chlorides. Exceptions include silver chloride, which is here, you can see, and hydroxides are generally not soluble, although there is a little bit of solubility. Sulfides are generally not soluble, but exceptions include ammonium sulfide and sodium sulfide. So you can see here, generally not soluble. There is a little bit, like in solution, but generally not soluble. Hydroxides are generally not soluble except when the cation is group 1A metal or strontium and barium. So sodium hydroxide is very much soluble. Calcium hydroxide is not. Iron hydroxide is not. Nickel hydroxide is not. So sodium hydroxide is something called a strong base. It is very alkaline, but we'll learn about acids and bases in Gen Chem 2. But the important thing here to know is that whenever something is a strong base, it means that whenever it is dissolved in water, it separates into its ions, it dissociates. It dissociates completely into sodium plus and hydroxide minus. Copper nitrate is a soluble salt. So that means that it is separated into its ions, so copper 2 plus and nitrate. So both of which dissolve well into water, and we end up with copper 2 plus aqueous and nitrate aqueous. So what will happen in the reaction of copper nitrate and sodium hydroxide? Well, we need to go and try and consult our solubility tables. So here we have the reaction of our calcium nitrate and our sodium hydroxide. Our calcium give calcium hydroxide and sodium nitrate. And so we need to determine if the reaction will proceed or what will be the driving force of this reaction. So we have to look up, is calcium hydroxide, is it going to be soluble or is it going to be insoluble? And so the best way to go about that is to go back to our solubility tables. But from the understanding that most hydroxides are not soluble except for those of group 1, so like for example, sodium hydroxide, we're going to assume that it is insoluble. Like if we thought about the iron hydroxide and the nickel hydroxide, those were both transition metals. They're both transition metal hydroxides. They were both insoluble. Copper is also a transition metal. So we're going to assume that it is insoluble. Sodium nitrate. So sodium nitrate, generally speaking, the nitrates were soluble. So we think that that's going to be soluble. And so the metathesis reaction here, or a double displacement or exchange or swinger reactions, show that the ions swap over. And so the driving force here is the formation of this precipitate, this insoluble precipitate, this calcium hydroxide. So we already did that. So the predominant species are going to be calcium hydroxide. So we already talked about this being insoluble, and then that this was most likely soluble. So it will leave us with sodium aqueous and nitrate aqueous. So these are the predominant species in our vessel after we're done, of course, not counting the water. We'll have the sodium or calcium or copper hydroxide precipitate, sodium plus aqueous ions, and the nitrate aqueous ions. So the full ionic equation here is copper plus nitrate plus sodium plus the sodium ions plus the hydroxide anions gives us this copper hydroxide precipitate plus sodium plus nitrate. So that's the full ionic equation, but these are what do you call it? Are spectator ions. And so the net ionic equation would be this, which is the calcium 2 plus the hydroxide gives us calcium hydroxide as a solid. Right. So what will happen? So we have, if we have lead nitrate aqueous plus or potassium iodide aqueous are mixed. So there's a demo, I think, on the website of the publisher. So you can, well, you don't need to do that. We can like apply our solubility rules to determine if these are going to be or what's going to happen basically. So we have lead nitrate plus potassium iodide. So write the molecular equation, write the ionic equation, write the net ionic equation, and determine what the driving force of this is going to be. And I think I'm going to leave it here. So that's something to ponder over the next little while. Okay, so last time we talked about Stoichia, or like reactions of chemical reactions. We talked about stoichiometric coefficients. We discussed how those always had to be whole numbers, and we needed to balance an equation by keeping the same number of atoms on both sides. So for example, in this equation here, this molecular equation, we have, for example, one lead, this Pb on the left-hand side, on the reactant side. And then we have this arrow indicating that we're going from reactants to products. And on the product side, we also have one lead atom. And if we were to do that for the rest, like potassium is also represented by one on, or well, two on each side, 2 times 1, 2 times 1. And we can do that for the rest as well. And so that's an important consideration in our chemical equations. They should always be balanced in that way. Now, we also talked about some solubility rules and how those could be used to kind of rationalize a little bit about why a reaction proceeds in the way that it does. So typically, if a reaction proceeds to produce a precipitate, like a solid, which would come out of the solution, then that is typically a driving force for that reaction, and it will encourage that reaction to happen. And there are various other rules that we also learned about the solubility of various halides, some exceptions to that rule, and so on. Like, for example, silver halides typically are not soluble, but most halides are in fact soluble. Halides being those with ions such as fluoride, chloride, bromide, and iodide. So in this one, we had this molecular equation where this lead nitrate is reacting with potassium iodide to give potassium nitrate and a solid here, a solid precipitate of lead iodide. And so we're being asked to write out the net ionic equation. So that is the molecular equation. So our total ionic equation is going to be this one. So it's going to be lead 2 plus 2 nitrate. So we're basically just separating out all of the different ions into their constituent parts. So here we have this lead, it's 2 plus, because as we saw like in the previous modules when we learned about common ions, nitrate is typically 1 minus. So that means that our lead, in order for that to be a neutral complex, that lead also needs to be 2 plus. So we have 1 lead and 2 nitrates because of this little stoichiometric 2 down here, which means that we have 2 of the nitrate ions. So we have 1 lead, 2 plus 2 nitrates. Both are aqueous, both are dissolved in water. And then we have 2 potassium plus ions. That's also aqueous, as we can see from our molecular equation. And then we have 2 iodides, which are also aqueous. And that gives us a product where we've also separated out all of the ions, the potassium ions, the nitrate ions, and then we also have this molecular species, this lead iodide. Now we don't separate that out because that is our solid precipitate. So we never break up any solid, liquid, or gas or molecular aqueous species. So for example, we would never break up water. We would never break up sucrose, things like that. In this case, we also don't break up these the solid because it is our precipitate. We can only break up things which are aqueous. So these are ionic to start with, like the lead nitrate. That is an ionic compound that we learned about in module 2, I think. And so that one is aqueous and can be split up into its constituent ions. Okay, so now we're being asked to find the net ionic equation. So this is the total ionic equation where we've separated everything out. What we want now is the net ionic equation. And so the net ionic equation is the one where things are happening. Basically, the species from the starting materials to the reactants are significantly different. Now, what we do is we look to see which ones do not change. And the ones that do not change are the ones that are in the same form on both sides of our chemical equation. So what we would do is we would look at, if I can get my pen, we would look at all of the different ions that we've written out. So we've written out lead 2 plus, and so we look and see we've lead 2 plus on the left-hand side. What form is the lead on our product side? And we can see here that it is no longer in the lead 2 plus state, it is now in the lead iodide, this Pb. Pb is lead iodide. And so that means that this will be included in our net ionic equation, and so will this. Then we look at nitrate. So we have nitrate on our starting material side. on the left-hand side, and we have nitrate on the right-hand side. They're both the same. They're both nitrate, nitrate. So those will not be included in our net ionic equation because those basically don't change in their form, and so they're not included. Then we look at potassium, that's also the same on both sides. And we look at iodide, and it's different. So it's iodide on the left-hand side, on the starting material side, but it is here lead iodide as a complex, a solid precipitate on the right-hand side. So it has changed its form, which means that our overall equation will be lead 2 plus 2 iodide gives lead iodide. So we cancel out the spectator ions, i.e. the ones which do not change in their form. There's still nitrate on both sides, there's still potassium on both sides. So cancel those out to yield the net ionic equation, which is this lead 2 plus aqueous plus 2 iodide aqueous gives us our lead iodide precipitate. And that's how we would go about writing out this net ionic equation. So whenever we write the molecular equation and the net ionic equation for the following reactions. So we have here silver nitrate plus barium chloride. So we're going to be asking which one is insoluble. So we can write out our net ionic equation. So it's going to be, let's get rid of that. Okay. So our net ionic equation would be what? Ag plus nitrate NO3 minus plus barium 2 plus these are all aqueous. I just didn't write the AQ because it would be a little bit time consuming for our session today. So we have silver plus nitrate product of silver chloride. So if you remember what I mentioned at the start of today, you'll know that silver chloride is in fact insoluble. And we could also consult our solubility tables, which are down here at the bottom. And so you usually will have access to those in any quizzes or final exams would require this, usually. Although I don't know in this if we're going to include those in Gen Chem 1 this time. And then, what was I going to say? So then we have barium nitrate left over. Barium nitrate is typically soluble. So it's most likely going to be remaining as Ba plus 2 NO3 minus, which means that this is not a balanced equation because this is our product here, barium nitrate. So we would have 2 of these, and then 2 of these give us 2 of these, barium, okay, balanced now. So we look and we see which ones are in fact on both sides in the same form and which ones are different. So if we look at our silver is different, so that's going to be included in our net ionic equation. Nitrates are the same on both sides, so those get discarded or canceled out. Bariums are the same on both sides, they get canceled out. So we're left with 2Ag plus 2Cl minus gives us 2AgCl as our net ionic equation. Okay, so that means that we're going to be left with silver chloride being insoluble. We can see that from our table here. So soluble compounds are typically are halide salts. However, silver is one of the exceptions. And lead are all their exceptions. Magnesium okay, insoluble is going to be draw out our net ionic equation. in order to be able to solve this. Now we find that we have our ammonium sulfate. So let's see, is that balanced? Let's see. So our products here are ammonium iodide and magnesium sulfate. So magnesium sulfate is NH4 plus. So ammonium is NH4 plus. So we got two of those. Plus our sulfate, SO4, 2 minus. Then we have our magnesium, or Mg plus, plus our 2 iodide ions, gives us our products, which will be ammonium iodide and magnesium sulfate. So we can consult also our tables here. So magnesium sulfate is a little bit of a strange one because magnesium sulfate can be a little bit soluble and a little bit insoluble. So it's the one that's going to be the driving force of our reaction. It's the one that's going to be the one which is going to be precipitated. So it's relatively soluble, but it also is a little bit insoluble. So ultimately, I guess in overall terms, we're going to be saying that neither is insoluble. So if we look at our net ionic equation, we have, in fact, everything being soluble. So our net ionic equation is going to be pretty much the same as our, what do we call this? Our total ionic equation. So our answer here is that neither is insoluble. Look at our table, we see that almost all salts of ammonia, almost all salts of iodides here are also soluble. So ammonium iodide is going to be soluble. Then magnesium sulfate. So almost all salts of or sulfate. Salts of sulfates are soluble in water, except these ones, but magnesium is not included here. It's calcium, strontium, barium, lead, and silver. Magnesium is, in fact, pretty soluble, magnesium sulfate. If you have enough water. So then this one, what is the net ionic equation for the reaction between hypochloric acid and potassium hydroxide? So this is the acid and this is the hydroxide. So we have a neutralization reaction here between the acid and the base. So we're being asked, so we know that our starting materials are this one. I could write out just the total ionic equation. ELO. Plus potassium, okay, plus So our total, we're separating out each one of the acids and the bases into their constituent ions. So their constituent ions include things like the H plus Cl O4 minus anion, plus potassium, the K plus hydroxide, which is the OH minus. That gives us H2O as a liquid. So that's our liquid. So that doesn't get separated out into its constituent ions, plus the potassium, plus the hydroxide. Sorry, not the hydroxide, perchlorate. ClO4 minus. Okay. So what we do here is we look at which ones are changing and which ones are not. So if we look at our H plus, that is changing because it's not part of the water. If we look at our perchlorate, that does not change. If we look at our potassium, that also does not change. And so what we're left with is our H plus, our OH minus, and our H2O as a liquid. So that's why it doesn't get separated out. And so our net ionic equation in this case is going to be B, because it's got H plus OH minus gives us H2O. The perchlorate and the potassium are what are known as spectator ions, and they do not participate in the overall reaction. Now they exist, but they do not participate. Okay. So HClO4 is a strong acid, and KOH is a strong base. We learn significantly about those. We'll actually discuss briefly acids and bases, but that's a much bigger topic in Gen Chem 2. For example, this is an example that they have on webpage. If you go to the interactive textbook, I believe that there is a demonstration of this reaction, or you could probably just find something similar on YouTube. So this is a reaction where barium hydroxide and sulfuric acid are mixed together. And then whenever that happens, you can see it has an effect on the electrical circuit, and you end up with electricity flowing. And so you can account for that by writing out the full equation. You will see a neutralization reaction because this is hydroxide base, and this is acid with the protons. So the protons and the hydroxides will react with each other to give water as the neutralization product of the neutralization of the acid and base coming together. And then you'll be left with barium and sulfate ions, and those barium and sulfate ions will be able to carry the current, as we talked about. That would make an electrolyte solution, which is something we discussed in the first session of Module 5. So acids and bases, we'll talk about here the definitions of some acids and bases. So like we've encountered them a few times so far. We talked about them quite extensively in the first session of Module 5, but before that we also talked a little bit about them. You may be familiar with some acids like muriatic acid, which is HCl hydrochloric acid. You also have things like sulfuric acid might be in the common vernacular, and so on. So the Arrhenius definition. So an acid is any substance that increases the H plus aqueous concentration in an aqueous solution. So for example, HX, where X could be any sort of anion, like for example, in this case, could be chloride. So it could be HCl aqueous, dissociates, that means it separates into its ions to give H plus Cl minus. So the Cl minus here is pretty much a spectator ion, doesn't really do much in terms of this reaction or any neutralization reactions. So that's this. So you can see that it does increase the concentration because we're producing some protons and H plus ions as we go through the reaction. And then a base, conversely, is any substance that increases the hydroxide or OH minus aqueous concentration in an aqueous solution. So here we have a MOH giving M plus OH minus. M generally is some sort of group 1 or group 2 metal. So in this case, it would be could be sodium hydroxide, gives Na plus plus OH minus. I have omitted the AQ, but you should always include them. So that would be an example. Sodium hydroxide gives sodium plus OH minus. That is increasing the concentration of the hydroxide in solution because it's producing it. So whenever we add sodium hydroxide to water, what ends up happening is that the sodium hydroxide separates. So it starts off as like a sodium ion and a hydroxide ion. They're together whenever it's a solid crystal. But if we add that crystal to our solution, what ends up happening is that they get separated as the water molecules interact with them and they go off into solution. And so we end up with sodium ions and hydroxide ions. The increase in the number of hydroxide ions by this separation. When they're together, this is not going to produce any more hydroxide ions, but when they separate, I've now got an extra hydroxide ion, and that is what increases the concentration or the number of hydroxide ions in solution, and that is what is going to give rise to a base in the Arrhenius definition. Now, the Arrhenius definition is quite narrow because it only considers aqueous solutions. It also only considers things which have protons or have hydroxide ions, but as we will see, that is not the limit of what makes an acid or a base. So then, I guess the more common definition that we'll use most readily, at least in Gen Chem, is the Bronsted-Lowry definition. And so this defines it, it builds on the Arrhenius definition. It is not significantly different, but it does build on it. So an acid is any substance that donates a proton, H plus aqueous, a proton, because the reason why H plus is a proton is because there is no neutron there. So there's also no electron, which means that the only thing in its nucleus, the only thing that it is a proton. It has no electron, it has no neutron, just a proton. To another species is an aqueous solution. So HX could be, X could be our chloride again, so it could be HCl, aqueous plus water gives H3O plus. So this is what's called the hydronium ion, and this is our representation of the proton. So in solution, the H plus does not exist, at least in aqueous solution, it does not exist. What exists is this form here, where we have sort of like, so this is our water, and then it will have like a hydrogen bond to the proton that is given up by the HCl acid. And so that's the hydronium ion plus X minus. X minus is the chloride, which is our spectator ion. And so we have H3O plus aqueous is equivalent to H plus aqueous. So the hydronium ion is equivalent to the proton in solution. So you can write it either way. Just be familiar that they mean the same thing. H plus in an aqueous solution is the same as the hydronium ion. So a base is any substance that accepts a proton in an aqueous solution. So for example, this is the major difference. So previously we were defining in the Arrhenius definition, a base is something which increases the hydroxide concentration. Now, a base is any substance which can accept a proton in an aqueous solution. And so that's why things like ammonia are bases under this definition, because they can accept a proton. So remember, if we go back to our atomic structure, our VSCPR, and our electron pair geometries and things, we will hopefully remember that, or even our Lewis structures, that the nitrogen has a lone pair. And so this lone pair can be used to accept a proton in an aqueous solution. And so we can then form another bond to this proton and then be positively charged here along this bond. And so we end up with what is called the ammonium cation is the ammonia. So proton plus ammonia. Ammonia is a proton acceptor. That's a base under Bronsted-Lowry theory. How many protons, neutrons, and electrons are in H plus? So if we remember, hydrogen is 1 proton, 1 electron. There are no neutrons, which means that it has a mass of 1, an atomic number of 1. So there are no protons in the hydrogen atom, or sorry, there are no neutrons in the hydrogen atom. And then whenever we remove an electron from the hydrogen atom, we get H plus, which is our proton, because whenever we have the neutral atom, we have 1 electron and 1 proton. If we remove that electron, all we have is a proton, and so we just have 1 proton. We have 0 neutrons and 0 electrons, and that is for H plus. So acids are any species that increases the concentration of H plus ion in solution, ionize in aqueous solution to form H plus. H plus is just a proton, and acids are called proton donors because they give protons to the solution. They donate their protons. So the examples that we normally have are HCl. Whenever we dissolve that in water, so HCl plus, for example, water, we get H3O plus Cl minus. So remember that H3O plus is the same as H plus. So this is why it's called a proton donor, because the acid is where the proton, this H plus, came from, and because our H plus is, or sorry, HCl is H plus Cl minus. So whenever that dissociates in solution, whenever it separates, we have a proton and we have our chloride, and it's that proton which is being donated, and that is what fundamentally is an acid. Bases then are any species that increases the concentration of an OH minus ion in solution. That's from our Arrhenius definition, and ionize in aqueous solution to form OH minus. So that's whenever we have, like, for example, our sodium hydroxide, we have our sodium and we have our hydroxide. And before we add them to solution, they are a crystal, which has both the sodium and the hydroxide in it. But then when we dissolve it in water, those ions separate into their sodium and their hydroxide. And so that is a process of ionization. And so bases are called proton acceptors. That's, for example, our ammonia, where it has a lone pair of electrons, which can accept a proton from an acid or from solution. So what is the definition of a strong acid? A strong acid completely dissociates into its ions. So a strong acid is, for example, HCl. So HCl, whenever it is dissolved in water, it completely dissociates. There is no HCl remaining in solution. It's all in the form of H3O plus and Cl minus. A weak acid does not completely ionize in solution, and so it only partially dissociates. So for example, this is acetic acid, and acetic acid vinegar will typically dissolve in water only partially to ionize to the hydronium plus the acetate, because it is a weak acid. So the structure of this is like so. So this is a carboxylic acid. So it's this proton here, which is the one which will be lost. So that is the acetic acid, and then the acetate then will be something like this. Basically just that structure with the proton removed, the one that I circled. Like so. That's the acetate ion. Acid and base strength. So strong acids dissociate completely in water to form their ions. They ionize completely. Weak acids partially dissociate in water. Most acids that you will encounter are weak acids. There are very few that are actually strong acids. Strong bases also dissociate completely in water. If they're like, for example, arrhenius bases. Weak bases partially dissociate in water. So weak acids, anything that is not strong. So strong acids are like HCl or sulfuric acid or chloric acid. So this is very important. Since weak acids ionize to such a small extent, the molecular species predominate. So that means that whenever we have our vinegar on our table that we use as a condiment for our food, that is a weak acid. And so in that water, that solution of acetic acid and water and whatever other sugars and flavorings that exist there, most of that is in the form of acetic, or sorry, acetic acid, this one, the molecular species. A small amount of it is like this, which is what gives us sort of like the tingling, burning sensation on our tongue that can add a lot of depth of flavor to some of our food. So since weak acids ionize to such a small extent, the molecular species predominate. So our acetic acid is mostly in this form here. So yeah, acetic acid, perfect example. It's our table vinegar. It is very important in cooking and for other things. It can also be used as a cleaning agent. So polyprotic acids these are the ones with more than one hydrogen proton that can be donated to solution. So for example, HCl and nitric acid, they're both strong acids, but they both only have one donatable proton. Coincidentally, acetic acid, this one, also only has one donatable proton. It has 4 hydrogens, but only this one can actually be given up to solution. These 3 here are very strongly bonded to the carbon, and so those do not dissociate. Diprotic acids are things like sulfuric acid and carbonic acid. Triprotic acids are things like phosphoric acid and citric acid. So, for example, sulfuric acid is something like this. Something like that. And then phosphoric acid and citric acid are triprotic acids because they have these 3 protons here, which can be given up to solution. They can be dissociated. They can be ionized there.